only it's, well, there's gonna be two more steps added to it, because in a basic solution, you can't end with protons in the solution. You have to, like, your protons are gonna be neutralized by hydroxide. And so if you get to the end of this, you have protons in solution, you redo it, because, again, that protons are an acidic solution, so we're just gonna work on those last two steps, which you see here, down towards the bottom. Once we get through our initial steps, we want to add hydroxides to neutralize the protons. We're just going to look at the equation, see which side has the most protons. We're going to add that many hydroxides to each side, combine into water, and then cancel out like terms. Okay. So here is the equation we're going to use. All right. So in the cyanide ion here, what do we want to call nitrogen? We need to start with oxidation numbers. And we're going to start with nitrogen because at least it comes from a group on the periodic table that has a common charge. -3. What do we want to call the carbon then? Not minus. Look at the overall charge. It's a -1 overall. Something plus a -3 gives me a -1. +2. Each oxygen, of course, is going to be a -2. 4 of those oxygens will be a -8. The manganese, what is it going to be? Nope. Nope. I have a -8. I need to end at a -1. +7. Oh, okay. Well, yeah, magnesium has a common charge of +2 based off the group it's in. But that's why I like to use these atoms, because you might not be used to manganese. No, I don't think I've used it with you guys. I usually like to use antimony. That's because some of them, the symbols don't even look like the element. Antimony is SB. And after having a British, well, we call them PIs, but advisor in graduate school, if I ever hear someone say aluminium again, I'm going to lose my mind. Okay. Okay, so our oxygen is a -2. Nitrogen we want to do next because it's in the column where it's going to be a -3. What is carbon going to be? I have -2, -3. I need to end at a -1. +4. Okay, this last compound, how do I name it? This is a neutral compound, so you can name this one. Manganese. So it's ionic. So you're not going to use the dioxide. You only use the numerical prefixes for covalent. So, and manganese is a variable charge ion. We've got to get you some caffeine before you come to class. Yeah. You either need glasses or you're about to fall asleep. Okay, so variable charge ion has to have what in the name? Well, so a variable charge, some metals can take on multiple charges. Like iron can be a +2 or a +3. It has others, but those are the most common. Some of your metals have common charges, like zinc will be a +2, silver a +1. So you neglect something in their name, but you put in other names that go with variable charges. This is manganese 4 oxide. You have to have the Roman numeral for variable charges. So remember, each oxygen is a -2. 2 of them gives an overall charge of -4. That means the manganese has to be a +4. Now, well, let's see. We see that the manganese was reduced and the carbon was oxidized. Okay, so that's how we're going to split this into half reactions. The cyanide is going to go to the CNO molecule, or molecule. Ion, the permanganate will become the manganese 4 oxide. Okay, now the next step would be balancing all the other atoms except for oxygen and hydrogen. But if you notice, the C, the N, and the manganese they're already balanced. So we don't have to do that. Now we're going to jump to using oxygen. I'll get it in a second. To using waters to balance my oxygens. Okay, so for the cyanide equation, I have to use one water to balance the one oxygen on the right-hand side. For the permanganate equation, I have 4 oxygens, then I have 2 oxygens, so I need 2 more, which is 2 waters. Now I have to balance the hydrogens that I just put in there with protons. Okay, so my cyanide will be my water, cyanide, CNO minus ion, and then I'm going to need 2 protons to balance out the 2 hydrogens on the left hand. Yep, on the left-hand side. Okay, my permanganate equation. I will need 4 protons. Put those on the left to balance the 4 hydrogens on the right. Now what I'm going to do is I'm going to say, well, what is the charge on each side of these equations? So my first one here, that's a -1. On the right side, I have a +1. For my permanganate equation, the left side is a +3, and the right side is 0. I do that because that tells me how many electrons I need and where they go. So for the cyanide equation, how many electrons do I need and where does it go? They have to balance at the same charge. 2 electrons where? On the right side. So that's going to balance both sides at a -1. What about the permanganate half reaction? Yep, 3 on the left. Because I want to take that +3 down to 0. Now I need to scale the electrons. Where are they going to meet at? 6. I need to multiply the first equation by 3, the second one by 2. So I'm going to go ahead and write these where I can add everything together. Okay, so that's going to give me 3 waters, 3 cyanides, 3 CNOs, 6 protons, 6 electrons. Then my second equation is 2 permanganates. 8 protons, 6 electrons, 2 manganese 4 oxides, and 4 waters. Now, again, like I said, you can either go ahead and eliminate electrons, or you can add first, then eliminate electrons. This is going to get pretty big, so I'm just going to go ahead and 6 electrons, 6 electrons. Because again, you have 6 electrons on each side of the arrow sign. Okay, so now let's add everything together. Okay, I think I got everything there. Now, here's where the extra steps come in. I cannot end with protons in solution. Now, you could go ahead and cancel out some protons if you want to. I usually don't because I wait till I add my hydroxides in so that I make sure I've accounted for everything. Now, how many hydroxides am I going to put in there? I need to I don't care if I have hydroxide left after I'm done because it's a basic solution. I need to neutralize every proton. What is the minimum number of hydroxides I can use to minimize the proton, to eliminate the protons? 8. And now, and I have to put that on, I have to put that 8 on both sides of the equation. It has to balance. Okay. So let me go ahead and put the hydroxides next to the proton. Oopsies, I need 8 of them. Okay, now let's look. Those 8 protons and 8 hydroxides will give me what? Now 0. I have an H. Yeah. Well, not 16. Yep. 8 waters. What are those 6 protons and 8 hydroxides give me? Yep. So 6 waters with 2 hydroxides left over. Okay, now on the left side, I have 8 water molecules and 3 water molecules. That's going to give me 11. And that's the end of the left-hand side. Now, right-hand side. Let's see, I have, I'll do that at the end. I have my 2 hydroxides. And then 6 waters and 4 waters will give me 10. Now let's cancel like terms. Okay, so those 10 waters will cancel out all but one of those. And that gets us to where we need to be. Now remember, at the end, you need to make sure all of your compounds have phases. Again, you can wait to put them back in at the end, or you can keep track of them all the way through. They need to be right. Water is a liquid. Ions are aqueous. And the manganese 4 oxide was a solid. That gets us our balance in a basic solution. So again, notice all the protons are gone. We have excess hydroxide, but that doesn't matter. We've neutralized all the acid. All right, who's enjoyed redox? It's just kind of a long process. Again, when you're working these, go back to the lists I gave you. Just follow them. All righty. Now we're going to start some stuff that, I mean, it's from quantum mechanics, but we're not going to go real deep into that. Okay. Hybridization in the localized electron model. What I want to start with is this notion of the sigma bond and the pi bond. These blue orbitals here on the left side, those are hybrid orbitals. Okay, you see the head-on overlap right in the center of the two carbons? That's a sigma bond. Your head-on overlap is a sigma bond. Now, in this case, and we'll talk about this when we get to sp2 hybridization, you see in the image on the right, you have the 2p orbitals that are sticking up and down below the carbons. So these are going to be 2p and 2p. Those leftover p orbitals, after hybridization is complete, that's where the pi bonds are formed. You see how they reach across and they form kind of a cage structure around the sigma bond? That's why your higher level bonds start to get stronger. This is a single pi bond. So right there, that's a double bond between those carbons. Keep in mind, as we go through, every single bond location gets a sigma. Okay. Once you start getting to double and triple bonds, where you start getting your pi bonds. So a single bond would be a sigma and a pi. A triple bond would be a sigma and 2 pi's. I like the irony of it because the more pi you add, the fatter the bond gets. So we're going to start talking about we're going to start with sp3 hybridization. Now, sp3 hybridization cannot form any pi bonds. You'll see why. But when it says sp3, that's because your atoms will have valence electrons. Those valence electrons will be in a mixture of, let's just right now, s and p orbitals. Your sp3 is going to hybridize, and it's going to take the valence s orbital, and then how many orbitals are in the p subshell? So count by odds, go spdf. No. How many orbitals in the p subshell? You can fit 2 electrons per orbital. Three orbitals. So you just SPDF 1, 3, 5, 7. So your p level has 3 orbitals. That's why this is called sp3. You're going to grab the valence s orbital and the 3 valence p orbitals. And that's why this can't sp3 can't pi bond, because after we form those, there's no p orbitals left over to form a pi bond. At this point, pi bonds are going to be formed by your untouched p orbitals. Technically, yes, d orbitals around metals can form pi bonds, but it's a whole ordeal. And we're not going to go into here because mostly d orbitals form delta bonds. The leftover p orbitals. You won't start seeing them until we get to sp2 hybridization. sp3, you're not going to see pi bonds. So when that s orbital and 3 p orbitals mix to form that's the word, to form the hybrid orbitals, it forms, so it took 4 orbitals, it forms 4 degenerate orbitals. Quantum mechanics, what does degenerate mean? What? Break down. Nope. That'd be like degenerate. Now this is degenerate. I don't want the definition you use for your brother or sister. What does degenerate mean in quantum mechanics? Nope. It means they have identical energies. Everything, if you have quantum states that are equal in energy, they're degenerate. We're going to start to use a lot of terms that you've heard other places, like the term ligands. I know Hardy uses that term. The chemistry definition is different, but not. If the fact that I like to refer to things as yes, but no, you're going to have to get over it because I'm a quantum theorist. That's just how it works. Until an observation is made, we're all living in a linear combination of possible energy states. So that's the whole thing behind Schrodinger's cat. You have a cat in a box, there's poison in the box. The cat is either alive or dead. You do not know if the cat's alive or dead until you make an observation and collapse the wave function. Until then, the cat exists energetically as both alive and dead. I'm not kidding. Look it up. That's Schrodinger's cat. Also, I like to remind people that we might be all that we might all die in a few minutes. We don't know, because if the sun goes nova, we won't know for 9 minutes. So you're seeing light from 9 minutes in the past. It could all be over. We just don't know. What a biologist told me one time, we're all of us are only ever 4 minutes away from death, but every time we breathe, we reset the clock. These are, I always love these little statistics. It really weirds people out. Yeah, I got a lot of that stuff. The stuff I don't know is military terminology. My two best friends from grad school were both Army EOD. And I guess they made like a version of Cards Against Humanity, but military style. I had no idea what the references meant. They just wanted to see what I would put together. Apparently it was really funny. So let's start talking about sp3 hybridization. All right, we're going to start with a molecule you should all know. CH4, what is that? Methane. So as you move on to organic chemistry, you're going to get lists of these. So this is an alkane. And remember, their prefixes have to do with the number of carbons. Meth is 1 carbon. So then ethane is 2 carbons, propane is 3 carbons, butane is 4 carbons. From there, it's easy because they use numerical prefixes. Pentane, well, that's 5. Hexane is 6. Heptane is 7. Octane, nonane, and decane. So 5 and beyond, it's easy because they use the numerical prefix. You just need to know those first 4 because they're a little different. Now, you have 2 more lists. You have, those are the alkanes. You have the alkenes. Well, not methane, that wouldn't work. But ethene, propene, butene, and then you have the alkynes. So ethine, propine, that's YNE. You know what the difference is between ane, ene, and ine? Think of it, that's true, but you're going about it the hard way. Think of it as bonds. Ane is single bond between carbons. Ene is double bond between carbons. Ine is triple bond between carbons. Yeah, so like your ethine would be 2 carbons and 2 hydrogens. Yeah. So whereas your ethane is 2 carbons and 6 hydrogens. So it's just single, double, triple bonds. So that's your little cheat sheet for organic. Okay, so let's talk about this. So we're going to do the Lewis structure of methane. Okay, now to figure out hybridization, count the regions of electron density around the central atom. Bonds count as electron density, lone pairs count as electron density. It does not matter if it's a single, double, or triple bond, it's one location. Okay? You're just looking for geographical location. How many regions of electron density do you see around the carbon? 4. 4 regions, sp3 hybridized. Now, something I'm going to throw in just to make sure you guys are getting it, because I don't know how much of it you did last semester. Molecular geometry. So do you know what geometry methane takes? Nope, tetrahedral, 109.5. But so the way we're going to work this, so there's what we call a generalized molecular formula, okay? And that is going to be A X N E M. And then you're going to start with your electron geometry, and that's going to be based off N plus M. Okay. Now here we have an AX4. So when you're looking at this, A is your central atom. X, and then here comes the biology term, are your ligands. In chemistry, a ligand is an atom or a functional group bonded to a central atom that affects geometry and reactivity. So you see it's like the biology term, but different. So this has an N plus M. So N is 4, M is 0, so it gives an N plus M of 4. So your X's are your ligands. Your E's are lone pair electrons, and it's a single lone pair. So a lone pair is not an E2, that's just an E1. But that's lone pairs on the central atom. If this had 4 fluorines on it, you don't count the lone pairs on the fluorines. You're only going to look at the carbon. How many lone pairs do you see? Those are your E's. Okay, now, an N plus M equals 4 gives you an electron geometry of tetrahedral. We have no lone pairs on the central atom. So the molecular geometry will also be tetrahedral. Once we start getting lone pairs on the central atom, the electron geometry and molecular geometry will not match. Okay, so now we know this is sp3 hybridized. Let's talk about how that happens. So for carbon, we have an electron configuration of 2s2, 2p2. I'm going to go ahead and write this out in full electron configuration. Okay, so how many valence electrons does this have? And how do you find them? Valence electrons are your frontier electrons that are going to be mostly responsible for your chemical reaction. It's in your highest level of what? Nope, not 6. Your valence electrons are located in your highest value of, so this time N is your principal quantum number, okay? It's in your highest value of your principal quantum number. Where do you find those? Those are your principal quantum numbers. Your highest value in this case is N equals 2. How many electrons do you have in the N equals 2 level? Nope, 4. 2s and 2p. So the valence electrons will look like this. Now you notice how in the 2p level I started filling those in with all up spins. What's that rule called? That one is Hund's rule. There's reasons for it, but you want to maximize the multiplicity, so you want to maximize the spin before you start pairing. So that means every orbital is going to get an up spin before you start pairing down spins, okay? If you take Chem 430 with me, that does start to change when you have metals and you have what's called crystal field splitting. So these are our valence electrons. Now I need to form the sp3 orbitals. And as I said, that means I'm going to take the s orbital and all 3 of the p orbitals. I took 4 orbitals. That means I'm going to get 4 degenerate orbitals. Now, look at the methane. How many sigma bonds do I need to take care of? 4. Everywhere you see a bond, there will be a sigma bond. So that's 4 sigma bonds. In your orbitals, your bonds are going to be denoted by a single electron. You're only going to have pairs in these when you have a lone pair. And we'll talk about that. Lone pairs have to go in hybridized orbitals, because hybridization occurs because electrons want to get as far away from each other as possible. They're repelling each other. And with the standard atomic orbitals that we have, if we start making molecules out of those, the electrons wouldn't be able to get far enough away from each other. Most of our molecules would just blow themselves apart. So we have to have this hybridization system. The wave functions have to shift in order to allow the electrons to space out from each other. Okay, so I have 4 valence electrons. I need 4 sigma bonds. That means I'm going to go 1, 2, 3, 4, because everywhere you see a single electron in a hybridized level, that's a sigma bond. For sp2, you're going to see electrons start to show up at the 2p level. That's a pi bond. Okay, that was a lot of fun. Let's do the next one. Ammonia. Okay, well, ammonia is an AX3E. You have the A, which is the nitrogen. The 3 hydrogens are your X's, and your lone pair, that's your E. So N plus M equals 4. So the electron geometry is tetrahedral. The molecular geometry in this case is not tetrahedral. Forget the lone pair, just look at the nitrogen and the 3 hydrogen. What does it look like? Pyramid, how many sides? 3. Trigonal pyramidal. Okay, now let's talk about its hybridization. How many regions of electron density do you see on the ammonia? 4. 3 bonds and a lone pair. So 4 regions, sp3 hybridized. Remember, every single bond is a sigma bond. We have 3 sigma bonds in there. Now, your nitrogen is going to have an electron configuration of helium as a core, 2s2, 2p3, which means its valence shell now you see how I've put a single electron in each of the p orbitals? If I had more, now I would start going back and pairing. So, which means I need sp3, so I'm going to use the s and all 3 of those p orbitals. You get 4 degenerate orbitals. Now, I need 3 sigma bonds and a lone pair. I have 5 valence electrons. 1, 2, 3, 4, 5. I need to use those to form the 3 sigma bonds and the lone pair. So sigma bonds, again, are a single electron. So 1, 2, 3. I have the 3 sigma bonds taken care of. I've used 3 of the 5. Means I have 2 electrons left. Lone pair. Again, as we're going through this, your lone here, it was in the hybrid level by default here. You're going to have to remember as we go on, your lone pairs are going to have to go in the hybrid level. Okay. Let's do another one. Let's look at water. This is an AX2E2. Again, N plus M equals 4. Tetrahedral. What is the molecular geometry of water? Not a pyramid this time. Bent. This is a bent configuration. And the electron and the molecular geometries, these generalized chemical formulas, really the only way to learn these is just to practice them and kind of memorize them. Now, how many regions of electron density around the oxygen? 4. So again, sp3. Your oxygen two s2, 2p4, that gives me 6 valence. So here's how I fill this. So I do the 1, 2, 3. But I have one more valence electron that I have to use. I'm going to go back and pair now, 4. Now, this is also sp3, so I'm going to use the s and the 3p's to get my 4 sp3 orbitals. And I need sigma bond, and 2 lone pairs. I have 6 valence electrons that have to be used. So sigma bond, that takes care of 2. Then lone pairs, 1, 2, 3, 4. Congratulations, you're now experts on sp3 hybridization. Let's move on to sp2. Okay, if sp3 needed 3 regions of electron density, 4 regions, how many regions does sp2 need? sp3 is how many less than sp2 is how many less than sp3? 1. So how many regions of electron density? 3. So sp3 needs 4, sp2 needs 3. So sp will need 2 regions of electron density. So it just steps down one each time. And so again, this time you're going to get the mixture of your s and 2 of the p orbitals with a 2p orbital left behind. So again, we're back to the ethine over there, or it's also called, or ethene, and it's also called ethylene. You might have heard that. Ethylene is another name for it, C2H4. So let's look at that. Now, again, everywhere that there's a bond, it's a sigma. When there is a double bond, I get a sigma and 1 pi. So I know that the carbons are going to have to sigma bond to each other and to each hydrogen. Hydrogen cannot hybridize because it only has the 1s orbital. That's just going to stay a sphere. Okay. The carbons can hybridize. Now, in this case, we have C1 and C2. If you're asked for the hybridization, you can treat each carbon as its own central atom. Okay. So look at carbon 1. How many regions of electron density are around carbon 1? 3. The 2 hydrogens and then the bond in the center. And it's the exact same for carbon 2. So you just go one atom at a time, treating it as its own central atom, okay? So that means carbon 1 equals carbon 2 equals sp2 hybridized. So again, our carbon now, since it's sp2, I'm going to use the s orbital and 2 of the p orbitals. I use 3 orbitals. I get 3 degenerate sp2 orbitals. And the 2p orbital I didn't use. Now, each carbon has to form 3 sigma bonds and a pi bond, and it has 4 valence electrons to do it. Now, the hint that I'll give you is your pi bonds have to go in the 2p level. Your hybridized orbitals will not pi bond. It's going to be the leftover p orbitals. So that's one of the valence electrons. Remember, everywhere we need a bond, we're going to put 1 electron. So that takes care of 1 of them. I have 3 valence electrons left to form 3 sigma bonds. How are those going to space out? Where are they going to go? Yep. 1, 2, 3. So that's 3 sigma bonds and a pi bond. Here's a fun molecule. Is it CH2O? Does anyone know what this is? Remember in high school when your teacher opened up the jar with the pig in it and that horrible, horrible smell? Yeah, this is formaldehyde. So when y'all get to anatomy and phys, you're going to get a lot of this. Okay, so let's talk about this. Now remember, your oxygen is going to have lone pairs around it. So my carbon, notice how I have a sigma, sigma, a sigma, and a pi. You have a double bond in the center. So the carbon's going to have to form 3 sigma bonds. The oxygen's going to, and a pi bond. The oxygen has to form a sigma bond, a pi bond, and have space for 2 lone pairs. So the carbon, what's its hybridization? How many regions of electron density does it have? 3, so it has to be sp2 hybridized. The oxygen, how many regions of electron density does it have? 3, the lone pairs count. So it's also sp2 hybridized. Let's look at how that happens. So our carbon, of course, we know we're going to get the sp2 and the 2p. We did that above. And so it needs 3 sigma bonds and a pi bond with 4 valence electrons. So sigma, 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 and pi. Okay. Oxygen. Six valence electrons. Those 6 valence electrons have to give me 2 lone pairs, a sigma bond, and a pi bond. So again, I'm going to get my sp2. My 2p's left over, well, I have to have a pi bond, so that's going to take care of one of the electrons. I need a sigma bond, so that's going to take care of another electron. That leaves me 4 valence electrons. That'll be my lone pairs. Your lone pairs have to go in the hybridized level so that they can get far enough away from other electrons to not destroy the molecule. To kind of give you an idea of how a pi bond works, let's look at the ethene again. If I just draw it with bonds, there in the center, I have that head-on overlap. So that's my sigma bond between the 2 carbons. Okay. I have another sp2, an sp2, an sp2, and an sp2 with my hydrogens bonded those. Again, head-on, so they're sigma bonds. I don't want to redraw this. So. Now, you remember that there was a 2p that we didn't use on each carbon. So there's the unused 2p orbital. Each with an electron in it ready to form a pi bond. So then what you get is these p orbitals reach across and they form this structure around the central sigma bond. So if I had, so like this one goes above and below the molecule. If I had a second pi bond, it would go in and out. So you can, so essentially these pi bonds are going to form a little cage around the molecule. So as we get going, next time we're going to look at sp hybridization. If you ever want to have some fun and look up a nice pi system, look up the pi system of the benzene molecule. I refer to it as the hamburger molecule. You'll see why. And it's not just because I'm a husky fella, although I do love hamburgers. But look it up. Look up the pi structure of the benzene molecule. You'll start to see these pi structures exist. They exist outside of the plane of the molecule. Okay, so we'll pick up with sp hybridization next time and have some more fun.